Our today's discussion is on Matlab simulation of a bidirectional circuit used to charge the battery from the grid and discharges the battery to the grid. This model can also be used as a demonstration of V2G and G2V operation in the electric vehicle. This is the basic circuit topology of a three-phase electric vehicle battery charger. At the input, we have a front-end converter, also known as active rectifier, which converts the AC grid voltage to DC, and maintains a constant voltage across the DC bus. Then we have a bidirectional buck-boost converter, used to control the battery current during charging and discharging operation. Now I will give you the specification of the complete system. Grid voltage 415 line to line RMS at 50 Hz. The filter inductance is 3 mH and capacitance is 30 microfarad. In the inverter bridge I used IGBTs. Value of bus capacitance is 5600 microfarad. MOSFET is used in the buck converter. Buck filter inductance is 20 mH. Output capacitance is 0.625 microfarad. Battery nominal voltage is 360. Switching frequency of both the converter is 10 kHz. Total rated power is 10 kW. Now I will show you the control block diagram used in both the front-end converter and bidirectional buck-boost converter. This is the control block diagram of the three-phase front-end converter. This controller is used to regulate 800-volt DC across the bus. This is the control block diagram used in the bidirectional buck-boost converter. This controller is used to regulate the battery charging and discharging current. Now we open the Matlab and start doing the simulation. Add a three-phase voltage source. This source we are using as the grid. Set phase-to-phase voltage 415. Frequency 50 Hz. Set source resistance and inductance, very small values. And base voltage 415. Add a three-phase voltage current measurement block. Here I am measuring phase to ground voltage using label VABC, and I am not measuring the current. Connect this block to the voltage source. Now we start connecting the LCL filter. Add a series RLC branch. Make it as inductance and set the value 5 mH. Connect the inductor in all the three phases. Copy this block. Make this branch as capacitor, and set the value 30 microfarad. Connect the capacitor in all the three phases. Now connect the inverter side filter inductor. Now add a current measurement block to measure the inverter current. Change its direction. And also flip the block, up, down. Connect this in all the phases. Add a go-to block. Change its direction. Give the tag name, IR. Similarly connect IY and IB. Connect the go-to tags into the current measurement block. Now we create the three-phase bridge using IGBTs. Uncheck this box. Add a in port. Connect to the gate terminal. Name it as PWM1. Similarly, connect to all the other gate terminals. Make sure that the name on the port appears correctly from PWM1 to PWM6. Now add a connection port. Keep the port location left. Name it as VR. Similarly, connect VY and VB. And change the port name also. Keep the alignment left for both. Now connect the port across the DC terminals. Keep its alignment right. Name it as VDC+. Keep this alignment also right. And name this one VDC-. Now add a series RLC branch. This is the DC bus capacitance and its series resistance. Set the resistance 1 milliohm and capacitance 5600 microfarad. And set initial voltage 800. Create subsystem from the selection. And delete all unwanted connections. Now connect the three-phase bridge to the LCL filter. Now add a from block and connect it as PWM1. Similarly, connect all the 6 PWM signals. Now add a voltage measurement block. This is used to measure the DC bus voltage. Add a go-to block. Name it as VDC. Add a MOSFET and make the buck converter. Uncheck this box. Add a series RLC branch. Set the resistance 0.0001 and inductance 20 mH. Copy the RLC branch. Here set the resistance 0.0001 and capacitance 0.625 microfarad. Now add a from block. Name it as buck. Connect it to the gate terminal. And similarly connect it to the other gate terminal and name it as boost. Now connect the battery. Set nominal voltage 360, rated capacity 300 Ah, initial SOC 50% and response time 1 second. Flip the battery block, left-right. Now add a bus selector. Add SOC, voltage and current into the bus. Add a go-to block. Name it as SOC. And similarly connect the battery voltage and current at the output of bus selector. Name it as IBAT. And name this one VBAT. Now we start connecting the inverter controller blocks. First add a from block. Name it as VABC, which is same as the grid voltage. Add a ABC to alpha beta block. Add a alpha beta to DQ block. Add another from block. Name it as omega T, where omega T is the output of PLL. Add a demix. Now add a go-to block. Name it as VD. And this one BQ. Copy this from block. Name this one alpha beta. And this signal will be used as the input to PLL. Now we connect the current transformation blocks. Take all the three current signals. Add a mux. Make number of inputs 3. Add a ABC to DQ transformation block. Make number of outputs 3. This one also need to make 3. Copy these from blocks. Name it as ID. And name it as IQ. Now we connect the PLL blocks. Add a alpha beta to DQ block. Copy this demux. Add a sum block. Make it sign minus plus. Add a constant. Set the value 0. Add API controller. Make the controller PI and set KPKI values. Add an integrator. This is the output of PLL, and this has to go to the other transformation blocks. Now we start connecting the DC bus voltage controller. Add a constant block. Set the reference voltage 800. Add a sum block. Make the sign plus minus. Take the voltage signal and connect to the sum block. Add API controller. Make the controller PI. Set KP 0.5 and KI 5. Copy the sum block and PID controller. Here give Kp as 25 and Ki 500. Here change the sign to plus plus. Add a gain block. Give its value 2 into pi into 50 into 10 e raised to minus 3. Connect IQ to the gain block. Change its name to VD. Add another gain block. Set the value to. Add a product block. Change the number of inputs. Connect DC voltage to the product block. Now to make Q-axis current controller, copy and paste all these blocks. Add a constant block. Set the current reference as 0. Copy this block. Rename this to ID. And rename this to VQ. Change its sign to plus minus. Now we start making the battery current controller. Add a from block. Select IBAT from the drop-down list. Add some block. Change sign plus minus. Add a constant block. Set the battery current reference 30. Add APID controller. Make the controller PI. Set Kp 0.005 and Ki 10. Limit the output between 0 and 0.95. Add a DC-DC PWM generator. Set switching frequency 10 kHz. Now connect the output of PWM block to the respective gate terminals of the MOSFET. Add a logical operator. Select NOT from the list. Now add a mux. Make number of inputs 3. Connect the controller outputs to the mux. Add a DQ to ABC transformation block. Copy the PLL output and connect to this block. Add a 2-level PWM generator. Set switching frequency 10 kHz. Add a D-mix. Set number of outputs 6. Now connect these outputs to the respective PWM signals of the inverter. Now add a power measurement block. Add grid voltage and current to this block. Add a scope. Open the scope settings. Change number of inputs and layout in the scope settings. Connect the grid voltage and current to the scope. Add another scope to view the DC bus voltage. Add displays to view the active and reactive power taken from the grid. Now open the configuration settings. Set solver type ODE23T. Add a power GE block. Set simulation type discrete and sampling time 1 microseconds. Here I made a mistake in the connection, so I will correct it now. Now set simulation time 1 second, and run the simulation. Here you can see that the active power is positive, which means that the power flow is from the battery to the grid. So the system is working in the V2G mode. Now let's wait to run the simulation 100%. Now I will show you the voltage and current waveforms. As you see, both the voltage and current are aligned in phase, which means we are injecting the power into the grid. This is the DC bus voltage during V2G operation. Now to make the system work in the G2V mode, that is, charging the battery from the grid, we need to make the current reference negative. Now again run the simulation. This is the voltage and current during G2V mode. As you see, both the voltage and current are aligned out of phase, which means power is taken from the grid. This is the bus voltage during G2V mode. And here you can see that the power is negative, which means power is taken from the grid to charge the battery. This is the end of this presentation. Thanks for watching.